much. So this is Bram from the Free University of Brussels, and he will talk about cross-level debugging for static analyzers.
Okay, thank you. So let me first start with talking a little bit about static analysis itself and why is it so difficult to develop debugging tools for. So some terminology, what does a static analysis do? Well, it takes some source code as an input, which we will call the analysis target. Then some analysis implementation will run some static analysis on this input, and in the end we will get an analysis result. Now, as a concrete example, you could consider a very simple type analysis. So let's say that as an input we get a program that computes the factorial of some number, and we run a type analysis on this program. We will get, hopefully, some kind of integer number as a type in the end. So this is what our analysis could predict. Now, usually what do we want of a static analysis? Or at least want of a static analysis that are, well, we want two properties, which is termination and soundness. And so what does termination say? Well, for any input program, we would like to terminate the analysis. So even though the input program does not terminate, our analysis implementation should terminate on that input program. Next is soundness. What we want is that the analysis kind of over-approximates the behavior of the program. It considers all possible execution states that the program could have when we give it to a concrete interpreter. Now, of course, it's very well possible that an analysis developer is not able to satisfy these properties because there are some bugs in the analysis implementation. And then, yeah, we could get a violation of the termination property, or we could lose our soundness. Usually, we see this reflected in the analysis result. Certainly for soundness, suddenly we might get a value that does not correspond to the expectations that we have about the input program. For example, a program that computes the factorial, it would be very strange if our static analysis would derive that the output of that program is a string instead of an integer. Then we would call that program or that static analysis unsound. So that is the kind of stuff that we can have for bugs in a static analysis. What do traditional debuggers do? Well, they would target the analysis code, or what we call the analysis implementation, but that is actually quite difficult, because what we have is two code bases. We have the inputs that we are analyzing at the moment, and we also have the analysis implementation itself. And usually what we see is that if we give the analysis a specific input, then we see some bug, but with other inputs we might not see the bug. So in essence, we want to reason simultaneously about the analysis target and the analysis implementation. Furthermore, it is not entirely clear where we would put things like breakpoints in our analysis implementation. Because the analysis implementation, it's quite large. We have an implementation that is a few thousand lines long. And so it's not clear where we would have these breakpoints to see our bug reproduced. On the other hand, when we look at a specific input program, like our factorial, perhaps we have a function string to number, which does not function properly or which doesn't have a good analysis implementation. And maybe it would be more interesting for a programmer that is developing our analysis implementation to put a breakpoint in the inputs of our analysis implementation rather than in the analysis implementation itself. And so, in related work, static analysis developers were consulted to see what their difficulties were while developing static analyses. And so there, the same debugging target mismatch was found, that we have these two code bases, the analysis target and the analysis implementation, and well, yeah, it's not very easy to reason about those simultaneously. And furthermore, the survey found that the generic visualizations and state inspections of debuggers are not adequate enough to debug static analyses, because the states of static analyses, they become quite difficult and very difficult to reason about, certainly if you can just only see the memory structures that we have in the analysis implementation. Rather, developers would like to have analysis-specific visualizations, like a control flow graph, so that you can see what the analysis is doing in terms of its current state. And so this is an idea that was put forward by these authors. However, one limitation of their work was that they didn't really consider the use of breakpoints. There is some suspension available, but you cannot really express conditions that you would need for breakpoints to be executed in the sense of conditional breakpoints, and I will explain in the next few slides why this is a problem for static analyses. To do this, I would like to give some background on how we perform our static analyses. So again, our factorial program, what does it do? Well, yeah, it computes the factorial, and for number 5 we get, when we execute this in a concrete interpreter, we get the value 120. However, this program does not always terminate for all inputs. For example, if we give it -1, our end condition is never reached. And so if we would just, as a static analysis, use a concrete interpreter, well, then our static analysis would not terminate. And to solve this issue, we usually go for abstract interpretation rather than concrete interpretation. And in this style of static analysis, we replace the concrete values that we have in our program with abstract values, such as types, and then run the program with that kind of values. And usually, we represent those things using mathematical lattices. For example, here on this slide, we have a lattice that represents a type domain. On the bottom, we have no information. Then we say that it's precisely an integer, boolean, of string, or any combination when we go up in the lattice. And so the goal of this structure is to make the state space of our abstract interpreter finite, so that our abstract interpreter always terminates on all inputs. However, this is also some kind of source of bugs, because we have to re-implement all primitive operations on these abstract values, such as multiplication, addition, and so on. So to show you how this works, let's go back to the implementation or the analysis of our factorial program. The end result would be int, as we would expect, and we arrive at this by replacing all concrete values with abstract values, such as the 5 that we replace with int. And the execution of the program continues. So we see that the variable x is also replaced in the condition of the if expression, and then also in the multiplication that we have in the false branch of the if expression. But this also shows our second challenge that we have in debugging static analysis. That is that our program execution becomes non-deterministic. And so what a static analysis would typically do when it does not have enough information to determine, for example, for an if expression, whether to execute a true or false branch, it would execute or explore both. A second ingredient of our static analysis is the modular static analysis. And so in this approach, instead of analyzing the program as a whole thing, we split the program into multiple parts. So for example, here, we consider the main function as a part or component of the application. Then we consider the decrement1 function as a component, factorial function, and that's it. And so the idea is that in that analysis, we could analyze those independently and then combine the results of them together. However, this is not always very trivial, because components are not really independent. They can call each other, for example. We have here main calls factorial, and factorial calls decrement1. And furthermore, they also share variables with each other. And when those are updated, we might also need to reanalyze one of the components that we thought were independent. To illustrate this, I have a very small example. So what you see on the right now is what we call a store, which is an abstraction of the program's memory. And at the moment, we don't have any information about the variables in this program, so everything is bottom. Now, let's say that one of the values in the store is updated, for example, in the decrement1 function, then it's normal that we have to reanalyze the factorial function because it reads the return value of the decrement function. And to do this, we keep track of a work list to remember what we have to do next. So then we go to the factorial function, which again has a value where the main function depends on, and then our story continues with a new iteration of the analysis, and we go to main, and then this is where it stops because main doesn't have any values that could flow back to factorial or decrement. This highlights the third challenge of having a debugger for static analyzers, and that is that it might take a while before we actually reach the bug in our static analysis implementation, because we might do many iterations before we get to a value in our store that triggers the bug that we are talking about. So these three challenges highlight the problems that we have, and we propose the following solution. So we propose cross-level history-aware and domain-specific breakpoints, and I will explain each of them next. But first, I would like to introduce our debugger interface, which is inspired by the survey that was done a few years ago. So at the top in area A, you see the code that we are analyzing, the analysis targets. In area B, we see the component graph that I've also introduced on the previous slide. And in area C, we see the visualization of the store. Now let's talk a bit about color coding we have here. So in blue, we have store addresses. And in green, we have the components that I was talking about a few slides back. And then in the store, we also have a specific color coding where we use the green parts for addresses that are just added to the store. And by just added, I mean between the current suspension of the analysis and the previous suspension of the analysis. And then in yellow, I have my updated addresses. So addresses that are changed between the current suspension of the analysis and the previous suspension of the analysis. So then, of course, we also have unconditional breakpoints. We have implemented them here as just conditional breakpoints, but with a true. This hashtag T means true, with a condition that always evaluates to true, so it always breaks. It's an unconditional breakpoint. But of course, this is not very interesting because, as I have specified earlier, we have this problem with our many iterations of our analysis before we reach the problematic part of our application. So we actually want to use a condition there. And for that, we use domain-specific conditional breakpoints. And the breakpoints that we came up with are all related to the state of the analysis. And there are three parts of the state of the analysis which are important to us: the store that I have explained earlier, the lattice to represent our abstract values, and then the work list to see what components are added to our queue to be analyzed next. And each of these categories have specific breakpoints associated to them. For example, for the store, we could ask the debugger whether the store has changed before the current suspension of the analysis and the previous one. To give an example of this, I have our factorial program again, and here the breakpoint only breaks when the value in our store stored on address x semicolon 4 is an integer. So we have two types of breakpoints here. We have the store breakpoint and the lattice breakpoint. Now notice that this breakpoint is placed in the analyzed code rather than in the analysis implementation. This enables us to use the control flow of the analysis, or of the control flow of the program that we analyze to place particular breakpoints. For example, here we know that this breakpoint will only be triggered when the factorial function is executed. If we would place this breakpoint in the analysis implementation itself, we would have a much harder time to only break when we reach the factorial function. So this makes the life of the analysis developer much easier. And secondly, even though the breakpoints are placed in the analysis code, it talks about the analysis implementation. here we refer back to a structure of the analysis itself, mainly the store. So the breakpoints, they are not just conditional breakpoints about the input of our static analysis, but they actually cross the boundary between the input program and the static analysis implementation. Of course, we have more predicates, but you can find a full list of these predicates in the paper. So now briefly, before going to how we validated our debugger, I would like to explain how the conditional breakpoints are evaluated. So basically, we have three parts. We have the debugger itself, we have the static analysis implementation, and then we have what we call a predicate evaluator. And so in the first step, what would happen is that the static analysis notices that the input program contains a break statement. Now, we don't evaluate the expression of the break statement in the static analysis itself. Rather, we pass it to a predicate evaluator. And the reason we do this is because our expressions, they shouldn't really influence the analysis result. Instead, they should only query about the analysis state, but not change it. So that's why we have this third component, the predicate evaluator. And in step 2, the expression is passed to this predicate evaluator, which then maybe one, twice, multiple times queries the static analysis itself about its state, and then decides whether to suspend the analysis or not by signaling true if the analysis should suspend and false if it should not suspend. To evaluate our approach, we implemented our debugger in a framework called MAF, which is the modular analysis framework, and we searched for real-world bugs in the repository of that project. And to do that, we looked for words such as bug or fix to find a particular set of commits. And you can see here that we have 3 commits, actually one more which is not shown on the slide, which fixes particular bugs in the analysis implementation. And then from all these commits, we selected 4 real-world bugs, and we also introduced a synthetic one, which you can find in the paper. And then we reintroduced the bug back into the current version of our framework. Keep in mind that the actual root cause of the bug was not known to the first author, and the first author also had to synthesize programs that would trigger the bug. And so the goal was then for this validation to see how we can use our debugging infrastructure for finding the root cause of the bug. To give an example here, we had a bug that resulted in an analysis that did not terminate. What the program does is not really important, but it just computes the sum of the numbers that were given to the sum function. And what we would expect if we sum 1, 2, 3, and 4 together is that we would get the value 10. However, our analysis does not terminate. And this is because, well, we actually didn't know. We had to find the bug, of course. But probably the reason for this problem was in how we triggered reanalysis of components. So what should happen is that if some value changes in our store, the component that depends on those values is added to the work list, and then it's reanalyzed. However, if nothing changes anymore in the store, the analysis should terminate. So let's see if that's the case in our example program. So at first what we did is we placed breakpoints on each function of the analysis target to see whether there was a single component that actually resulted in our non-termination issue. And so as you can see in red, we have the line that is currently suspended on. And in the beginning, of course, it goes to the main function, then it goes to the compute function, it goes to the sum function, and then it goes to the aux function. And each time you have seen that in the background of my slides, the store was updated. We had these things highlighted in green, and we have these things highlighted in yellow to see what things changed and were added in the store. Now this becomes actually interesting at this point. The auxiliary function, what it essentially does, it implements a recursive loop over a list. And so this takes quite a while to stabilize. You have all these elements of the list that you have to consider, or 1, 2, 3, and 4. And so it takes a few iterations to reach that point. However, what we notice is that the analysis does not stop when the store has no other values that change. So here we have the store, which has only white lines, which means that no value has changed between the current suspension of the analysis and the previous suspension of the analysis. So this suggests that the bug is indeed in the auxiliary function and has something to do with lists. Now, we have placed breakpoints, and actually unconditional breakpoints on each line in the functions, or on each function in the program. And what we have seen is that this approach is fine to find some indication where the bug could be, but of course, it takes quite a while to reach the actual problem. And what we have seen is that with these unconditional breakpoints, we have to step through the program into the next breakpoint for a total of 16 times. So here is where our conditional breakpoints shine again. So what we noticed is that the analysis does not terminate for the aux function, and we have also seen that the aux function has just a single argument that it depends on, so that's the only cause of our bug probably. So what we do is we wait until the store has no changes anymore, and then we will break the analysis. And this is expressed in our conditional breakpoint by using the store changed breakpoint together with our L address, and then we invert it so that the analysis only breaks when the store does no longer change. And this results in an analysis or a suspension of only 6 times. Then we ask ourselves, for all of these bugs, how often do we use our conditional breakpoints? And so what we see is that the what we call regular breakpoints on this slide, which are just unconditional cross-level breakpoints, they are often used first to find the bug where it could be, and then the domain-specific breakpoints are used to further limit the region where the bug could be, and also to reduce the number of iterations the analysis has to take before we reach the problematic behavior. In future work, we would like to extend the set of meta-predicates that we have for expressing the conditions in our breakpoints. And then it could also be interesting to make them stateful instead of having only a hand-picked set of history-aware predicates such as store changed. And then a static analysis, it could be quite interesting to go back to a particular step in a static analysis and see what was going on there. So some kind of time-traveling debugging could be interesting to be introduced there as well. So in conclusion, we had 3 challenges that we would like to solve, which was the challenge of 2 code bases, the challenge of having this abstract domain and the exhaustive behavior of the static analyzer, and then the problem of having too many iterations before the bug is reached. To solve this, we introduced domain-specific history-aware cross-level breakpoints that allow the developer to reduce the state space where it needs to search for the bug and find the root cause of the bug faster. Thank you very much.
If you have questions, please come up to the microphone.
Thanks very much for your talk. It reminds me a little bit of Code Prober, right? That in attribute grammars where you can look at the input program and then move around and see what are attribute values on that part of your tree or property. And so, you know, that was another case where you're looking at the input to your system and searching on it instead of in the code of the system. So, but here you're doing, is it mostly abstract interpretation? Is the sort of things you're thinking with these breakpoints that as you're abstractly interpreting the program, that's when the breakpoints trigger?
Yeah. So yeah, the abstract interpreter traverses the program, and then when it finds the breakpoint, it will suspend the analysis based on the condition. So that's what we mainly focused on. However, you could also implement different kind of analyses using this approach. And also perhaps this approach can also be applied to a certain sense to, I think it was attribute grammars or something in the code prober paper. So yeah, that could be very interesting to see what the synergy between those two approaches could be.
Because you're not. I was just thinking if you're doing something that's more syntax driven, then I'm not sure what the breakpoints are as much, right? That you sort of aren't evaluating in some way or interpreting the program, but I don't know. It's
they are sort of a part of the analysis. They're literally like statements in the analysis. And now,
yeah, I suppose if you, you could label a statement, say now when you do something here, right, as opposed to an execution style. Okay. Anyway, thanks. It's very interesting.
Still time for another question?
Could you share some thoughts on, well, I mean, in general, you call it static analysis, right? But in general, this is applicable to pretty much any language processing, which is hard to debug. So quite often this is done with some kind of traversals or strategies or some sort of abstract way to say, this is what I want to do with this data structure. And yeah, it would also be nice to have some debugging capabilities when you can say, well, I want to rewrite it innermost, but after you've rewritten it 3 times, then please let me examine what you've done. So is that the kind of direction where you think of going, or is it impossible to express in your way, or what are your thoughts?
In a sense, we have these breakpoints that consider previous states and histories and so on. And so in that way, you could think about changes in data structure and so on that could also be used using these breakpoints. But like directly, I don't really think that there is an application. But yeah, I mean, the approach itself could be used further. What I would also like to talk about maybe is, because you mentioned that it could be applied more generally, is that you have kind of the same problem with just concrete interpreters, for example, where you want to debug those. And there you have a similar approach in other papers as well, where they create domain-specific visualizations to, for example, show how the stack of the concrete interpreter looks, or the stack of the program that you are interpreting, instead of the stack of the concrete interpreter, and so on. So I think there is also some overlap, and yeah, there could be ideas that could be shared between the two.
Okay. Thank you for a nice talk. So I was wondering, when you looked at the bugs in the analyzers, did you try to classify the different bugs into like, some of them seem to have to do with not triggering recomputations, and were there other kinds of bugs that also appeared? Yeah, so, well, we didn't really have that many bugs to create a very big or large classification, but indeed we saw different kind of bugs. So the one that I showed was about non-termination, but what we also frequently have in our static analyzers is problems with the abstract domains and abstract values. If you implement your multiplication in the wrong way or some other primitives, then that might also have some very strange results on the analysis implementation. So I think termination is an issue, the abstract domains are an issue, and yeah, currently those two are the most frequent bugs that we found in a static analyzer. So something about the soundness basically and about the termination, that's what we usually see.